Hello, my name is July Thomas at the University of Florida. Today I'm going to be talking a little bit about our results from the IllustrisTNG simulation. Specifically, we looked at the accretion onto merging supermassive black holes in IllustrisTNG. Now, we're not able to probe the merging event directly because that occurs way below our resolution scales. But what we can do is constrain the in spirals to sort of aid EM searches for LISA events. As I mentioned, my advisor is Dr. Blecha. I'm at the University of Florida. The IllustrisTNG simulation is a cosmological simulation suite run on the Arepo code, and we look at just TNG 100-1, which is just a single run from IllustrisTNG. Before I get into my results, a little bit of background. We started off looking at the merger AGN, or active galactic nucleus, connection. And I'm going to share with you two prior results, one observation and one simulation. On the left-hand side is a result from Saeb et al., where they took the WISE color matching criteria and applied them to the Sloan Digital Sky Survey. And they compared the AGN excess as observed, excess compared to isolated supermassive black holes. And they compared that AGN excess to the separation of two black holes. And what they found is the red and blue here are two different infrared bands, the WISE color matching criteria. The red one is W1 minus W2 is 0.8, and this one, the blue one, is 0.5. And the green is visible light, the visible spectrum. And so what we see is, while there is an increase in the AGN excess with decreasing separation in visible spectrum, there's a much more dramatic increase in the infrared. And what that indicates to us is that there is potentially some obscuration occurring there, making it difficult for visible observations. On the right-hand side, then, a simulation. This one is not a cosmological simulation. This is a Zoom simulation, sunrise simulation run on the Gadget 3 code. And this is just a run of two black holes undergoing a merger. And on the top panel, we have the AGN luminosity versus time. This vertical line here indicates the exact time of the merger. So what you'll notice is that not only does the luminosity become more variable near the time of merger, but it also peaks right around then. And the bottom panel gives you the column density, and you'll notice that the column density likewise peaks around the time of the merger. The point here is that obscuration is a difficulty when we're looking for potentially a difficulty for observers when seeking out supermassive black holes. Now, there are some techniques which are promising for observations, obviously, to find these. But specifically, what we're going to look at is the benefit of the cosmological simulation, as we know with certainty the behavior of black holes. So here's just a quick run through of our results. The key questions that we set out to answer: first of all, how much is AGN activity associated with mergers? And secondly, how much black hole mass growth is associated with mergers or is dependent on mergers? So we'll start with AGN activity. Throughout this talk, I will be sort of using as a stand-in for an active galactic nucleus. I'll be using the Eddington ratio, the accretion ratio, and the accretion rate within the Eddington ratio. The Eddington ratio is the Bondi accretion rate versus the maximal Eddington accretion rate. And on the left-hand side, we've taken all supermassive black holes and all the snapshots of IllustrisTNG 100 and plotted them versus just the black hole mass. And we get a kind of good idea of the distribution. You'll notice that there's an overdensity, kind of the beef of the distribution is up around 10 to the negative 2 for the Eddington ratio. And that drops down a little bit after about black hole mass of 10 to the 8. And that's as black holes are transitioning from quasar-dominated to radio jet-dominated. And down here we have some black holes which are accreting at very, very low Eddington ratios. And so yeah, so those indicates, you know, black holes that are very inactive as far as the accretion onto them. Now, if we just pick out the merging supermassive black holes, the way that we did this is we took each merger event within IllustrisTNG, and we took the merger remnant, went to the next snapshot after the merger, and pulled down its accretion rate, and turned it into the Eddington ratio. And what you'll notice, first of all, is that there are very few black holes accreting at these really low rates, and that also most of these remnants are hugging the top of the distribution between 10 to the negative 2 and 0 until we get into that radio mode dominated regime. So this is our first hint that remnant supermassive black holes or merging supermassive black holes have an enhancement in their accretion. Now we can go ahead and analyze this data, and this is a visualization that I'm going to use throughout the talk, so let me just run down for you real quick. These crosses, the horizontal bar is the bin width, and the vertical bar is the interquartile range, so it's 25th to 75th percentile, and then the intersection here is the median, or the 50th percentile. So if we take that data from those last two plots, put it on one plot, we have now the merging supermassive black holes and the non-merging supermassive black holes, so it's actually the total population minus these merging black holes. And what we've done now is we plotted that Eddington ratio versus the redshift, and what we see is that at high redshift, there is quite an enhancement for the merging supermassive black holes compared to the non-merging, but that enhancement decreases with redshift. So the question that we asked ourselves right away was, are there any subpopulations of black holes which exhibit a separation throughout all of cosmic time? And we ran the numbers, and what we came away with was that if we look at small supermassive black holes, so small for the simulation, less than 10 to the 7 solar masses, in gas-rich environments, those supermassive black holes, you'll notice, exhibit an enhancement all the way down to low redshift, as noted by an offset in the IQRs of those bins. And we've also included on here all non-merging, so the gray crosses here, or the red crosses from over here. That just sort of gives you an idea of the behavior of this subpopulation relative to the total population, and that. But the point here is that, yeah, for these supermassive black holes explicitly, there's an offset throughout cosmic time. Now, just to shore this up, what we did was we wanted to take this a step further, and in order to do that, we took each remnant supermassive black hole and matched it to 10 non-merging black holes in the same snapshot as the remnant, that had the nearest post-stellar mass. So same snapshot with the 10 nearest post-stellar masses. And what we came away with was this matched catalog. We reran that same analysis from the last slide. And when we look at all black holes in that matched catalog, what we see is that that big enhancement at early times is decreases a little bit. You'll notice, remember, this is the gap from before. So much less of a gap there, but a relatively similar enhancement at low redshift. But once we look at this specific subpopulation, small mass gas rich, low mass gas rich, we see again that enhancement is maintained fairly decently down to low redshift. So yeah, so that is sort of a rundown of what we could do with the snapshot data. Now, the snapshot data is one set of data. It's a more common one that you're used to pulling down from simulations. And snapshots are really good because it gives you a whole breadth of data, a whole bunch of different statistics on events and particles and things like that. But those snapshots only output about once every 200 megayears for the IllustrisTNG simulation. So just as a quick rough example, what we have here is these two near the seed mass supermassive black holes, only a little bit bigger than the seed mass. This is actually the earliest merger in IllustrisTNG 100. And I'm just giving you a rough picture of the information that we get from the snapshots concerning this merger. This is a little bit of a dummy example here, but the point is just that with the snapshots we get the Eddington ratio or the accretion rate sometime before and sometime after. We see that there's some apparent enhancement, but in the Illustris simulation we get another set of data, and this data is not as broad as the snapshot data, but it does provide us a 100 times time resolution, 100 times finer time resolution. So this black hole details allows us to create a picture of the merger that looks something like this. And this is clearly much more detailed, much more dynamic. Now, in this specific merger case, this guy up here, this remnant black hole was consumed some short time later in another merger, but there are roughly 9,000 major mergers in IllustrisTNG 100. So what we can do is, the first thing we did was we took all of this merger, this high time resolution merger data, and we set all the black holes relative to their exact time of merger. The time of merger here, by the way, is the black hole merger time from the simulation, which as I mentioned before, we cannot resolve the in-spiral, so it's actually some time between the galaxy merger and the actual black hole merger time. However, we took all of these, lined them up to their time of merger, and ran the same similar analysis that we've seen before. And so here we have from a giga-year before and after merger, and this is for high redshift mergers. And what we see is that these black holes show quite an enhancement in their Eddington ratio right around the time of merger, and actually just a little bit after the merger. So that's pretty compelling. Now, the thing is, if we take this down to lower redshift, what we'll see is that the size of that enhancement decreases as we go down to low redshift. This has to do with black holes. The biggest thing is depleting the gas, the gaseous fuel that they have available to them for accretion. Yeah, this is still pretty compelling analysis at high redshift, but we can also do something really, really cool now that we have this high time resolution data. So what we did was we took that high time resolution data, and for each merging event, we looked at the time around that merging event and calculated the accretion that occurred just close to the time of merger. And we did that for each merging event and then traced each of those mergers down to the remnant black hole at redshift 0 by constructing a black hole merger tree. And that enabled us to look at the amount of mass that is gained during mergers. This is how we answer the question of how important mergers are for black hole mass growth. And this plot here is just one example. This is preliminary result, kind of ongoing right now. But we have the proportion of Z0, redshift 0 black holes and the percentage of mass gained within 125 megayears of merger. And we bin these up according to black hole mass. And what we see is if we look at low mass black holes, so less than 10 to the 8th solar masses, we see that only 0.2% of those black holes gain at least 20%. So that would be right here. So the green and orange lines, the orange you can barely see, so those two comprise only 0.2% of those black holes that gain at least 20% of their mass during a merger. Now, if you go up to the more massive side, so anything bigger than 10 to the 8th, which would be your red and your purple here, those black holes, in that subset, it's 16.7% of those black holes that gain at least 20% of their mass during a merger. Now, it should be pointed out that 86.7% of Z0 black holes have never undergone a major merger in their lifetime. But the one thing that I will say is that even if you control this, again, very preliminary, but even if you only look at black holes which have undergone a merger, there's still a difference here where the larger a black hole is, that tends to indicate more pronounced role of mergers in building the mass of those black holes. So I'm going to go ahead and leave you with my takeaway. The biggest takeaway is that if you have high time resolution black hole data like we do here, and you can combine that with the large volume and the large statistics of a cosmological simulation, you get this powerful new probe into the merger AGN connection. Also, as a quick note, there are 3 other talks from folks in my group up on the Lisa whatever virtual event. So I've given you some quick links there. And if you have any questions, you want to leave them on the Lisa page in the comments, so I'll get back to them when I can. Thank you, everyone, and have a good day.